Jesus. Don't think you need that. All right. Okay. All right. So basic testing. What we're going to talk to, like I mentioned before, in briefly, it's like we're going to talk about basic testing vocabulary, basically. So that's what we're going to talk about today. So we're going to take a look at how to define testing a bit more like academia terms, basically. So we're going to take a look at what is testing, and we're going to talk about fault, errors, failures, infection, propagation, testability, test cases, input domain correctness, reliability, test levels, and test types. So lots of definitions today. So we're going to take it like piece by piece. So this is a game that Daniel developed. So I'm not going to talk too much about it, but so basically what they had a problem. Certain times it crashed, basically. So I will let you watch his English lecture because it's better to hear him speak about it and his experience about it. But basically, he went on a 6-month hiatus searching for a bug, basically, causing a blue screen of death. So, instead, I'm going to mention my background instead, and when I first came into contact with testing, and that was around 99, 98, 99, something like that. I was working as a support technician at SPCS. It's now more known as Visma or Spiris, which they are trying to rename themselves as. So I'm not sure if they have succeeded yet. But. So basically, as a support technician at the SPCS, we got the chance to do some testing. And because at that time, back in those days, we actually sent the product burned on the CD to the customers. So we sent a lot of those CDs, basically. So the program needed to work. We needed to make sure that the program actually worked when we sent it to the customer because it was quite expensive to send it out. There was basically no internet infrastructure back in those days. There was some. We still got fax and stuff like that. We faxed help out to our customers, basically. But at some points in time, we got to help out with the testing. We had a testing department, basically, in that company. I think they probably still do, but it's slightly different nowadays. I haven't worked at Visma for a very long time, and they do a lot of different products now. So what happened is that basically what we did is that we installed the new version on our computers. We ran the program according to like a sheet of paper. These are the steps that you should go through, basically, and double check that everything works. So that was my first encounter with testing. And we did find bugs during those test sessions, which then was reported to the developers, basically. So that was my first encounter with testing. Then I worked for quite some time in the industry. I've almost racked up like 20 years now as a developer. So testing has come and gone in popularity. Nowadays, we do testing as developers. So we write unit tests, and we do integration tests sometimes as well, depending on how the infrastructure, how the company looks, basically. It depends on what type of testing you do as a developer. So what is testing? Testing is to show that a program does what is intended to do and to discover defects, preferably, before it is put into use. So we need to make sure that our program basically works, right? So we don't want customers to say, this doesn't work. So because then you lose the customers. So what it is intended to do. Have you done a programming project course? Okay, so have you written specifications in that? Yeah, okay. So here are the specification and the requirements. That's where they come in actually, because you specify the requirements for your program. So based on those, we know what the program is intended to do, right? So show that the program does what that program does. Run the program. So we need to run it. So testing is most of the time a very dynamic thing to do, right? And you probably do it without thinking that you actually do it. So you run your program and you run through certain things when you start the program. Okay, this does this work? So you probably don't think about it as formal testing, but you actually do it, right? When you write the program, you need to verify that, okay, yeah, it seems to be working, right? So at least I do when I program. So I usually run the program and run through the aspects of it. So that's part of our testing experience, but you can formalize it a bit more. So yeah, discover defects, compare actual and expected behavior. So from the requirements, we know what the expected behavior is. And when we run the program, we get the actual behavior, right? So specific input on there. Yeah, so test case. So basically we have, if you have specific inputs, so back again to so we had this paper when we did the testing. So we followed specific test basically that was based on the requirements that we had. So based on specific inputs, we get expected output, right? So if we put in some value, we expect something out that should be the correct. Otherwise, it's a bug, right? Yeah. So this is basically what it is, testing. It's like checking. So you will hear something about, so there's testing and there's checking. We will get to that a bit later. But so testing checks that system conforms to the requirements. So that's the basic of it. So remember that. So what happens is that we get confidence. Okay, so we test the system to get confident that it actually works as we intended it to work. And this is super important. And that's why a lot of companies nowadays do spend more time doing unit testing, integration testing, and all those kind of things, is to basically have confidence in that the product actually work when we launch it. Another part of it, it's to discover problems, defects, bugs. So that's also a thing. But we also use it to understand the system more. It's like sometimes you can do exploratory testing where you randomly you sort of randomly run through the system. So if you have like a testing role in a company, you might do this more often. As a developer, you probably don't do it as often. But developers, they can use the testing code as a guide to understand the system. So, and unit test, for example, is exceptionally good at this because you can take a look at like a method of a function, and if you find the test for those, you can get the basic understanding of what are the requirements basically for this function. So it can be used in that way. It's a pretty good start. Usually when I start going into a new system, I do tend to take a look at the test and see how those match basically the implementation. So yeah, so and this can lead to us getting a deeper understanding of the system. Basically, we can figure out So when you do assignment 2, when you take a look at the open source projects, basically, this is what you basically will be doing. You will take a look at how the testing is done, and also take a look at, is there a way to improve it, or how do they run it? Can I understand the system based from the testing aspects of it? So yeah, we'll get to validation. Okay, validation. So basically, from the specifications that we have, we need to validate, are we building the right project? So, and this is, so validation, and we'll talk about verification just in a little bit. So there are two different things. Validation is that we're building the right thing. This is like a communication between us as a developer or a company, for example, and do we need meet customers' expectation, for example. So this is the validation. Are we building the right thing, basically? So that's part of it. This is kind of hard to test, actually, because it can be a very high level. For the game, for example, I think Daniel mentioned that is it fun to play? How do you test that? You have to run the game and actually go through it, right? And what's fun for me could be not so fun for you, for example. So we have different aspects of it. But they had like a producer that said, this isn't fun, basically. So this is more customer oriented, but it's also part of testing, but at a very high level, and usually involves a dialogue and communication with the customer. So testing is a lot of communication as well. So like I mentioned before, like unit test can be communication to us as a developer, like a documentation and stuff like that. Usually developers are at that level. I worked at certain companies that did some integration testing and stuff like that as well. And also trickier systems where you use like tools like Cucumber and stuff like that, when you actually you work the interface basically through a tool and those. But usually developers, we deal with unit testing level testing, unless you are explicitly need to test the system in a different way. So most companies, or at least bigger companies, usually have dedicated testers, and they do more like run the entire system at a different level. Yeah. So this is the needs and expectation that the customers have, basically, and this is the implementation. Hopefully these should overlap as much as possible. So, like I said, is it good enough? We get this from the specifications, and a lot of it is communication. All right, verification. So verification is, are we building the product right? So does it work as this little part, does it work as intended, basically? Usually we talk about something called, sorry for jumping around a bit. No, I will mention that later. Checking something. Yeah, so once again, the requirements of the system is the one that guides this as well. So when we did the validation, they can be more fussy. Here we need to be more to the point, basically. So we try to find faults in the code by finding some inputs for which the behavior output of the system is incorrect. So for certain inputs, so we try to feed inputs into the system and see if it behaves as we expected. If If it doesn't, we have found something that is faulty, right? Yeah. So there's something called program verification. That's a totally different thing. It's even more formal. I think that's mathematically formal. So you don't need to. Verification, what you should remember is that validation is like building the right thing. And this is more like, are we the product right? So here we verify that it for certain inputs. So verification is for certain inputs, do we get what we expect, basically. All right, so here's the tricky part. So let's say that this person here, it's like a product manager for some. He thinks about the product. Okay, I want a square, I want a circle, that's green. Let's write some specifications for this. It should be an orange rectangle. It should be a green circle that is drawn on top. Okay. This specification, and there's a lot of things that needs to be in order for us to be very certain on that we get exactly the same thing, right? So this specification goes to the developer. So he thinks about this in a different way. Okay, I agree, orange rectangle, green circle on top, right? No problem. Fix this, implementation looks like this. That looks fine, right? So, and the testing here is expected rectangle color orange. This will pass, right? This testing. The rectangle is there. It's not a problem. But we're missing a lot of things, right? So here's the original version. Based on faulty, lacking specifications, we get a vision from the implementer, and then we get an implementation that is totally out of whack. So specifications need to be a lot more detailed for us to be able to test them more. So the testing definitely needs more as well. We need to test, okay, does it contain a green circle? Nothing about this this will work, right? So what this will say is that, okay, if we run these tests, no problem. Everything is hunky-dory. No, it's not. This looks weird. Not even maybe the same orange. Well, in this case, they actually test the orange color. So, but is that the only thing? Shouldn't we test the size, where the different parts are located, and stuff like that? So this becomes like we need to communicate the specifications very, very much better than this, right? So in order to do those kind of things. All right, so specifications. So this is the specification, this is the implementation. So where they overlap, this is like the code. This is what we have actually done according to the specification. This is the entire implementation, right? The yellow parts. So this is what we actually have coded and stuff like that. So here in the green part is where the specification and the implementation overlaps. So that is the system that we're interested in, right? So, and if we find something that doesn't, the implementation and the specification doesn't match, we get a fault, right? So here are the things that we can actually test because we have a specification around it. These things here, that's outside the surprise area, we don't know anything about. It could be like framework code. It could be something that the developer thought was funny to do, so, but it wasn't in the specification, so it's still there. I've seen a few things that looked really weird. That shouldn't be there in certain implementation. And the blue part here is the omission. That's specifications that we haven't implemented yet. So the faults are only in the code that are implemented according to the specifications, but return something that's unexpected, right? Those are the faults. Okay, so yeah, sorry about my throat is a bit. I hope I last all day. So testing and checking. So basically, what we usually do when we program and we implement the system is probably this, right? Not this. We do this. We do checking. So we're not doing testing. We're doing checking. We're verifying something. We enter input, check output, compare with expected. So what we do, we check the system when we code it, basically. So it's manual, it's repetitive, it's pretty boring, and we usually automate it as soon as we can. So that's always the goal with those kind of things. If we can, there are certain aspects that are exceptionally hard to actually automate, the testings and stuff like that. So it can be hard to do those kind of things. Testing is the process of coming up with a test instead. This is kind of creative. It's a creative process, basically. And so why should we run a test? What are the goals? What are the requirements? What does the code look like? What part of the system? System under test. So system under test is something that you will encounter a lot in this course. So system under test is the part we are testing. It can be a method, can be a function, can be something bigger as well. So this is something that we need to think about. What are we testing? What is the system under test that we're actually testing about? So we need to ask those questions when we create the test. And also what are the inputs and what are the expected behavior? So testing is more to figure out how to do this kind of things. Then we do run the checking. So testing is figuring out how to do the test. Checking is the actual behavior that we do. So testing is to come up with ways to exercise, run the system with the aim of finding faults. So testing is dynamic, even though some quality requirements might use static testing. It's like, okay, so do you understand this part, the static testing part? So if the lint example, for example, is the code formatted correctly? Those kind of things. So that can be part of it, basically. So checking enters input and compares expected behavior to actual behavior. Validation, more general goal, and verification conformance to requirements. So like higher validation, higher loftier goals, basically. Bit more fuzzy. Is the game fun? It's a good reminder. Is the game fun? How do you do it? It's hard to do verification. Is the game fun? Because that can vary. Verification, conformance to requirements. So verification is harder. It's like stricter in that aspect. All right. So that was the first part. Okay. A lot of new stuff. I have to sip of this. Then we're going to move on to faults, error state, failure, infection, propagation, testability. So a lot of new words, right? Or also, this is kind of formal because this is a course about testing, so it's like formalized testing. A lot of these things you might not encounter when you start working, but they will be there. Like they might not have this formal language for it, but when we talk about this, we want to have like a formalized language around these kind of things. So you will basically, when you start working in the industry, you will be able to connect these things. Like you will create this context for you. So, all right. So fault, defect, bug. Okay, anyone knows what this is? Oh, it's the first bug. In the old days, they had like relays, actually magnetic relays for the first computers. So, and the first bug was actually a bug that crawled in between the relays, so it didn't hook up. So you got something. The first bug was actually a physical one. So things have changed slightly since then, I would say. Okay, so static flaw in a program code or state can be environment, database persistence as well. But bugs can be in a lot of places and can be tricky as hell to find. But in this case, this is a super simple, simplified example, but you will see why we use it. So we have an add function, and it takes two integers and returns a minus b. So it's fairly simple to see where the problem is, right? In this case, but envision that it's more complicated. So in this case, the minus sign is the static fault. It should be a plus sign, right? So we know, for discussion's sake, where the problem is. So, but we want to get the program into an error state, right? So in order to find the bug, we need so when we encounter the bug, we get an error state basically. So the program, when we run it, and if we run 3 and 4 as the input, we get an error state because the sum will be wrong, right? So and then we say it's infected because of that, basically. So but we have certain cases where we actually don't see the bug. So if we have 3 and 0, this still works, right? The sum is correct for this kind of input. So if you test it and you put 3 and 0, it works, right? So we don't encounter the error state here. So it's those are the things that we need to think about. So in certain points, it might actually work. So, but in order to find this, we need to. So reachability is that we reach into the code to the right place in the code in order to actually test it correctly. So we need to be able to get into that part. This can be slightly tricky because sometimes you have like internal functions or methods that you use to implement certain things. It's like a helper function inside of a class or a module or something like that. And that's private. Usually you can't access those. So you have to go through like an external part. And those can be quite tricky to find. So we need to figure out a way to reach into the part that we want to execute, basically. So in our case, it's the add method, which might be pretty simple. Usually it's like a public function, then it's not a problem. So, and then we need to have it so altered the program state into a bad illegal state that's result in an error state, basically. So we put some input like 3 and 4, and we get -1. It's kind of unexpected. So, but we need to call it with a non-zero b because if we call it with a 0b, all of a sudden it seems to be working, right? So reachability, we need to be able to get to where the possibility problem is. We need to be able to infect it in a way, and then we need to be basically the error state needs to be brought to the surface so we can have a look at it. So propagation is like to lift that part of the situation. So that can also be tricky. Like I said, if you have like a private function, it might be difficult to actually reproduce it in certain cases. And the propagation is because we need to figure out that if we have a failure, we need to be able to observe that failure. And this can be kind of tricky. So not every error state ever surfaces as an output. So are they the same? Is there a difference on the squares? They are the same size, but do they have the same color? I think there is one that is one like the next like one level just towards another end, basically. So it's slight. You don't even most of the people don't see it. I don't see it. So for me, those are the same, right? But if you have a test where you actually check the RGB code, then it would fail, right? Because there's a difference between them. So, and those are the tricky parts here. What are we actually testing? Like, this is the tricky parts with testing. It can be like for us, yeah, it looks fine, right? So not every failure is observed. Some are very hard to observe, like this one. And in testing, we need to be able to observe the faults, right? We need to observe the failures in order to figure out, okay, what actually went wrong. Otherwise, it's kind of hard to fix it. Let's see. Oh no, did it change? Okay, so let's see. So goals of a test case is that so we need to be able to control it, and this can be quite tricky. There's a lot of like there was a lot of talk about you should have like 100% coverage of testing, for example, for a program. And coverage, by coverage, I mean it's like you exercise every part of the code, basically. So I think we're going to talk about coverage in later lectures, but yeah, basically you want to exercise the whole system. And that's kind of super hard to go and do, actually. So certain parts are exceptionally difficult to control when you develop a different type of applications, basically. And if you develop a web application, for example, you want to be able to test it through its user interface, right? So otherwise, how do you exercise the actual interface, right? So the front end, you can have separation between the front end and the back end, for example, but you want to be able to exercise the system through its front end in order to get certain aspects of it. So these are kind of hard because there are specialized programs that you can use where you can specify, okay, press this button that has this text on it, for example. But it's kind of hard to test, is the button blue? Unless you specify, has it this hex code or anything like that, for example. So you get it, at some level, it gets very hard to test certain things. it's kind of hard to control it, but we want to control it as much as possible. Otherwise, it's really difficult. So we need to be able to reach the fault. We need to be able to produce the error state, and we need to make the error as visible as a failure. So if we have observability, able to see what the application is doing. So controllability plus observability gets testability. So the testability is kind of tricky to do in certain aspects. That's why I was trying to explain about the web interface, basically. There are tools, but they are kind of hard to use. I've tried a few, but they're kind of tricky. There are also certain frameworks that you can use, like Jest and stuff like that. And they can do certain parts of it, but kind of tricky as well. Yeah, so, and once again, we need to reflect this back to specifications and requirements that we have. So, controllability, able to steer the program, what we are testing. Observability is that we can actually see what comes out of it. And these plus, if we have those two, we can test it. So, all right, accuracy. Okay, so once again, so if you have, like you have a unit test that tests one method, you have higher accuracy because you can isolate the fault pretty good. So the add function, for example, if we can exercise that directly, we probably have a very high accuracy. But if you have to access the add function through an interface where you have to put in some certain inputs, like a React front end in order to access it, then you might have to do a lot of other things, right? In order to get to that. So the accuracy is much lower in that case because the fault could be in other places. So it's harder to isolate it the bigger the program is, basically. And if you have to jump through a lot of hoops in order to get there, it's kind of tricky to narrow down where the fault actually is, right? So we want to get as close to the code as possible to get the higher accuracy as possible. And this can be kind of difficult at certain times. Yeah. Traceability, how well can we connect failing test to the code under test, which code is tested? So in certain cases, this is kind of cool. Okay, if we have the code that we are testing. In certain times, we don't. And that's called black box testing, basically. It could be like an external API that we need to access in order to get certain information, for example, and that we might not be able to trace that fully. So, or it could actually be an internal microservice as well that you need to contact in order to get some information. So you need to be able to trace that. So that's one of the tricky parts with microservices, actually. So it's doing the traceability in the testing part. So, for example, if you have like a function, you have like a class that calls a microservice in order to get some response for it, you need to be able to actually to find the failure, where the failure is. You need to be able to trace it from your program through the microservice and then to the response, because anywhere could be where the problem is, basically. So microservices is tricky to use. They were in all the rage at one point in time, and then all of a sudden people said, no, now we're going back to monoliths again because and I think this is one part of it, because it's hard to trace, actually, because you need to do certain things in order to do that, because you have to have if the call comes to the microservice, basically you need to be able to trace that call in your logs or something like that, and you need to be able to follow every line of it. So can be tricky, very tricky. Yeah, and once again, how can we connect that to requirements? So we comes back to requirements again. A lot of it is because basically the requirements are the things that would guide testing. So how do we create our tests? So from the requirements, we need to figure out this kind of thing. All right. Fault is the static bug that can lead to an error state if it's executed. So the fault infects the state if the state is changed to an illegal one. For the error state to be detected, we must surface the output to be observed. Finally, as a tester, we must observe and make a judgment that's not what is expected. Yeah. So in the end, we are the ones that judge. Is this correct? Is this not? Basically. So yeah. Any questions so far? I've talked a lot. Does this make sense to begin with?
That's in black box text. The testing won't have access to the code.
The tester doesn't have in black box testing. Yes, correct. We can't watch the code basically. So it's like you send inputs in and you get an output. I think we have a slide at the end on black box testing basically. So, but in the gist of it, it's like that. You don't know anything about the code basically. So you look a bit sleepy, so I'm thinking we're gonna pause the recording and we're gonna take a break. And let's get back 5 to 11. All right, cool. Resume. Okay, so a lot of new terms, I guess, and we're gonna add a few more. So let's see, need to make like this, and okay, test case. So let's say we have our system under test is this function. And the test case here is we have an input X and an input Y. We have an expected value of 5, the actual value we get from actually exercising the system under test, right? It's like we talked about before. So we get the actual value, and here we compare the actual to the expected value. So if it works, we say, okay, it works. So this is like an exceptionally primitive test case. You can do it like this. You probably did once upon a time, back in the old days before all these unit frameworks in some way, if you wanted some sort of. But what's this missing? It's missing something, right? What happens if it doesn't work? Nothing. We don't get an no, it didn't work. So we need information on why it didn't work, right? So it might have been better to have like an exclamation mark if they are not equal, for example. It would be better to sort of print something. So, but nowadays we have a lot of nice unit test frameworks, for example, that helps us do these kind of things. So I think this is the JavaScript version. This is probably a JUnit, and this is probably something like in C# or something. So there are similarities between these frameworks, but how you put your test cases basically boils down to this. You have a system under test. You input some values and you check the output basically. So that's the gist of it what we want to do. We want to find the faults, right? So if we control the input, we can check the output and compare that to the specifications that we have. So these frameworks are quite similar in structuring. They're usually called X unit frameworks because X is basically where you replace the first letter, and it could be like for Java it's JUnit, for example. For Elixir it's EX unit. So but similarities are very sometimes. So as I mentioned before, you might need to do, in order to get to the point where you want to be, like you want to get to the add function basically, you might need to do a lot of things. You might need to sort of create, in Java, for example, might need to create certain objects in order to access certain parts of that class that you actually want to test. So you need to create the object, you need to exercise the method, and then you need to sort of check the output. So most of these X unit frameworks lets you do like setup specification basically. So it has usually it is like you have a piece of code in the beginning that sets up certain parts, and then you run certain tests basically. So we will talk about that more when we talk about yes, question.
Some things I can access even private fields and private classes in Java. Is it true?
So the question is that if you can access private fields and private classes in Java. I don't think so.
Yeah, you are
You-
able to.
you can?
There's
Okay.
specific frameworks where you basically in Java, I mean, Java has this weird file structure with all these subfolders.
Okay.
And you can basically create a folder above the main folder, I think was it, which is tests, and then continue to structure like the main Java structure.
Okay.
And then these files inside it, if they have the correct name, have access to private fields, so you can have proper
Interesting. Okay. So I was wrong.
Awesome.
So it's possible in certain frameworks, isn't it? I'm unsure if is it JUnit framework or
I'm just
No.
not entirely sure, but
Okay.
it's basically, I think I know, like, if you develop an app for Android, for example, the default framework, I think, includes something like
Okay.
this. And but I'm not sure exactly what it's
Yeah.
using.
Okay. So it might be possible in that case, as the gentleman in the font process. So it's quite possible. Those are usually tricky to find to get into in certain aspects. So at least it was. So if that framework solves it, then yay! Unless it's super expensive to run, who knows? So yeah, but the principle basically is the same. Sometimes you need to like create certain a lot of objects in order to actually get to the point that you want to test. So you might need to jump through a bit of hoops in order to get there. So this might be deeper down, and you need to propagate it up in order for us to observe what went wrong, basically. Yeah, so the components, as we saw, we have a system under test. In our case, it was the add method, basically. We have explicit, so we pinpoint the input that we want to give it, right? In order to control it. So as I mentioned before, we need the controllability in order to actually do the test in a good way. And then we check the actual and expected output bit. So we have an expected value that we want to see, and that can be anything from an actual value to, okay, we expect this to actually throw like an exception, for example. So we can test those things as well. So we expect it to crash, here. So we want to test that. And yeah, so, and then we observe the output basically. So, and then that leads us to, so the observe part here is connected to the oracle. So the oracle is the one that decides if the observed behavior matches the expected behavior. In most cases, it can be us, for example. When we automate the unit test, for example, we have an assert function that becomes the oracle, right? So we can assert that in these cases. So, and as we saw with the orange squares, if you remember that slide, for example, this can be kind of tricky. And yeah, so those kind of parts, like the orange square, when we take a look at it, this oracle aspect can be kind of tricky. And you can have a different opinion about the square. For example, you could be fine with it from your oracle perspective, and I can say, no, it's not. So it depends on what we're looking for when we test. So this can vary a bit, but we have like, in the end, someone has to decide if it's correct or not. So, all right. Just gonna. All right. So we have a more formalized version of this. So specifications. So we'll come back to this a lot, right? Because the specifications is the ones that will drive our testing. It will drive what tests should we run, how should they be formatted, and all those kind of things. So, and also determines the expected output that or the desired behavior that we want. So, but the specifications are also used by us as programmers, right? We write the program, and sometimes we write errors in the code. I have done a lot of them during my years, so it happens. No one's perfect. And that might lead to faults. So the program does produce the actual output, like when we run the program. So once again, testing is the dynamic aspect, or the checking part is the dynamic aspect. We need to run the program in order to get these kind of things. Just analyze the code can, in certain tools, help, but in most testing aspects, we need to run the program in order to get the actual output. So program produces actual output, which leads to hopefully something that we can observe, and then the oracle make like a decision here. So that's the formal process of it. Okay, so now we come to even trickier parts. So reproducibility. So we want to be able to test to run deterministically. We want them to end in some, and have the same result for the same output. For the same input, we want the same output, basically. So this is super important when we run like automated unit tests, for example. But it's not always the case. Can you figure out some things, for example, that when it goes wrong? Any idea on where can the problem be that the same input produce a different output? For me, a super classic case is dates. Dates. Sometimes you want to have today's date in your test, right? But if you run that today and then you run it tomorrow, those days are different, right? So not the best thing to do in a test, but I've seen it done. So and it can produce what's called flaky tests, because this will vary So the input looks the same, right? We send today's date in, but the output will be different, because most likely be different, because it's all of a sudden it's a different date. And the really tricky ones are the ones when you do leap years and stuff like that. Those can be really fun to find. Yeah, so we get a flip here, basically, because the input looks to be the same. And in some cases, we actually can have values that actually do be statically same, right? You send A and B, for example, in the static aspect, but the computation inside the system under test does something that might be using, like, for today's date, for example, inside of it. And all of a sudden, if you run that on a Sunday, we'll see that in the slide in just a minute. So you can get a different output. So in order to reproduce it, we need to be able to control, and you need, yeah, we need to be able to control a lot of it, basically. So, and this can become quite tricky. So here's an example, basically. This is from previous course, so it's kind of old, but it still feels value. So we have a test case. Usually when you do this, you mark them like this, like test case 1.1, stuff like that. Navigate to page. Here's a description. If you read it, it gives you a description on what you want to test, right? It should show this, and then you have input. Okay, what do you need in order to run this test? Okay, you need to clear the existing cookies. Okay, fine. You need to navigate to the site. Okay, that's the next step. So these are the tests. When I did the testing at SPCS, for example, these are the kind of tests that we got, but it was more like longer, because it was like you should put the following values into this form and stuff like that. So it can be quite extensive, the text, in order to follow all the steps, and then you get the expected output, basically. So this is a very short one. Okay, so we have the input, what we need to do. We have the output that we should verify. This is an image of the output, basically. So output next to the text not logged in is shown. Okay, yeah, good. A form for login is shown. Looks fine. So it's a verification, and today's date is shown at the bottom. Okay, no problem. Right, so this could be one of the test cases that would verify, okay, does the form actually shows up? In some certain frameworks, we can try to automate this. We could say, okay, it should be an input here and here. For example, we should have a login button, so we might be able to get it. But visualize is trickier, right? So we need to be able to visualize and see this. So, but some, when they ran this test, got this output. Yeah. So we get an unexpected output. So, and in most cases, like 60% of them, nothing, not a problem. So, and 1 in 65 actually found this bug. So what happened here? Well, it's kind of simple. It's actually a programming error in this case, because he misread the documentation, basically, when he wrote this. So his week starts on a Monday, but the framework's week starts on a Sunday. So we got a problem here. So most likely this was run on Sunday, so we don't get a value here. So it's a miscalculation basically on the format. So most likely it's like a zero value or something like that came up. So it can be tricky like this, because you actually, in order to see this, you have to run it on a Sunday. So he who programmed it always ran it during the week. Then it worked fine. This was not a problem. And all of a sudden, some student ran it on a Sunday. And it's a bug there. So dates can be exceptionally tricky to deal with. So it's one of the hardest part actually in programming altogether. And not to mention time zones. That's even horrible. So the tricky part also can be like the interpretation of the test case. So we had a specification a few slides ago, basically. And so was this very clear? Do you think this was very clear? It's pretty clear, but it could probably be better in some cases. I don't have a good example on what could be better, but apparently someone misinterpreted it, or just basically clicked, does it conform or does it go through, basically. So it was a verification. So validation of HTML and CSS, for example, some pressed yes and a few pressed no, and some so it is kind of hard, these kind of things, especially so if we're not clear enough on what we want to test, we can get some very difficult answers, basically. So, but yeah, flaky tests is basically the name for when the output varies in certain cases. So if, when the input is the same but the output differs at certain cases, then you get a flaky test. It's quite common, unfortunately. Big programs like Chrome has some flaky tests, for example, as well as some companies that I work for also has flaky tests. So when you run the test suite, sometimes it can be tricky because it can vary, unfortunately. So like we saw, the time of day when we run it can actually encounter this, because if you ran the test suite in the morning, for example, at one company that I work for, it failed. Certain test fails actually did fail. And but if you ran it a bit later, it worked fine. So it's weird. Timing, it could be, yeah, some timing issues can cause this. For example, communication issues, hardware and software. If you have different versions of it, like different node versions can cause unexpected failures. So that can be tricky. For example, the order in which you run the test cases can also have effects. So there's a lot of things that can actually causes this flaky test, basically. So so it can be tricky. They are super tricky to actually fix, because you need to figure out when does it actually fail. So and then that's a treasure hunt in itself. But it could also be something like we misinterpret actually what the test is for. So what are we supposed to test? So we need to be very explicitly clear when we communicate the test cases to those who actually perform the test, to them who do the checking, basically. So if you have like very unclear specifications, then you get unclear testing, and then you get a very unclear test output as well. So, and then you can basically have faulty test as well. But yeah, So it's not necessarily bad programmers. If the test fails, it could be like miscommunication. A lot of things that we do around testing is communication. So we come back to that. Basically, it's like communicating. How do we test these? All the kind of things. So, all right. So some more formalization. So I highly recommend watching Daniel's recorded video from 2013 as well, because you get a different perspective of all these kind of things as well. So do that. That's my recommendation. It's not very long. It's like 2 hours. You can speed it up and it should be fine. So definitions. Input domain is the set of all possible inputs a program P is known as the input domain or input space of P. So that sounded exceptionally formal. So if we take the add function, for example, you had two variables, two integer variables, for example. So both of them can be all the integers available in the system, right? So any input value. And this can be trickier if you have like a programming language like JavaScript, for example, because it's not statically typed. So you could send in anything, right? A function in A should produce something very different. So certain programming languages increases the input domain exponentially as well. So Elixir is also like a dynamic language, but you can sort of specify certain aspects of it. Correctness, a program is considered correct if it behaves as expected on each element of its input domains. So in order for a program to be correct, we need to run, for the add function, we need to run every integer combination available. So that's kind of impossible to do, right? Just for the add function. So how do you test correctness of a form in that case? You can't, right? It's kind of impossible because you can basically put whatever in it. So correctness is not the goal. It's more have this reliable. It's like we're looking for reliability in the thing. So and the reliability of a program is the probability of its successful execution on a randomly selected element from its input domain. So we have certain values, we run them through a test, for example. So if we take a form, for example, again, so the add function, we expect them to be like integer values. We don't expect it to be a function or something like that. So if we test a few of them, we can reliably say that, okay, yeah, this seems to be probably going to work. So depending on how it's formed, it's how the method is constructed and stuff like that. The reliability percentage can vary quite different. But for a form, for example, it can be, we expect the users to enter their name if this says name, not like the complete work of Shakespeare, for example. So we can reliably say that, okay, if it takes a name, a string of a certain length, for example, we can reliably say that, okay, yeah, this seems to be working. But sure, you could put Romeo and Juliet in the name field, for example. But so exhaustive testing is almost pretty much impossible for most applications. So, and like I said, just with this add function, you have quite a lot of numbers to go through in order to test that. And I would probably say that most computers will take a very, very long time to run those tests. So you can't exhaustively test your computer programs. You need to select the number of tests so that all the bugs are revealed, basically. So basically, this is what we want. So we need to figure out what kind of test cases do we want in order to figure out the reliability of the program. So, and that can be everything from a few test cases to maybe like 20, depending on how much reliability we need. So it depends on what you want to test. So with that said, this also, the software purpose guides the testing effort as well. So if it's like a game like Age of Conan, which when it released had a lot of bugs in it, maybe it's okay. Sure, we want it to work completely, but if you get like an invisible horse, yeah, we need to correct it later on. But so a game is compared to a rocket guiding system. See, I can. So basically, it takes off, and all of a sudden, at a certain speed, it decides to turn 90 degrees, and oof, it doesn't go so well. So kind of more expensive fault in the code, I would say. So you might want to test those a bit more. So fortunately, no person were on the rockets. It was a satellite only, but still quite expensive. There are certain areas where you probably want more exhaustive testing or close to exhaustive testing. Pacemakers, for example, comes to mind. You don't want them to have faulty software, for example, and that would be really nasty. So the purpose of the software also guides this effort, basically. So if it's something that people can die of, you probably want to test it more. So, but if it's a game, you can probably do a little less testing. So, okay, final part. Test levels and test types. So I have talked about a few of these already, but so it goes from lower to basically higher. So unit testing is coaster code, right? It's a method, functions, class, those kind of things. Integration testing, then you come up another level. Here, all of a sudden, you need to work together with other systems, other modules, microservices, for example, and stuff like that. So then you will come to the integration level. System testing. Now we run the whole shebang, basically. So integration testing can also be like front and back end integration, sort of. System testing is more, okay, you run the entire system and you exercise it through its interfaces, basically, in different aspects. So slightly different. I would say they're also in time consuming because this is pretty fast. Most organizations and companies actually have the developers run unit tests on their local computer before they push the code, basically, which is preferable. Integration testing takes longer. It's not certain they actually can run this locally in integration test because you have to most likely install different types of system. You might need extra microservice installed on your computer, basically, and you have to redirect. So this is more time consuming. System testing is definitely more time consuming because you need to exercise the system in a running environment. This is usually done through like a test environment. If you do a web application, you start a test environment and then you run system testing through them. Beta testing. Now you actually push the code and you have some of your customers basically do, or for a game, for example, it could be people that signed up for beta testing of a game, for example. But yeah, it is certain aspects that you want to test for a game. Can we have some simultaneous people online at the same time, for example? What happens? So these are the kind of things. But you have more or less, this is kind of finished. The system it's pretty much finished here, like, or at least a version of it. So, and usually there are people not inside the organization that run the beta testing. Example. So acceptance testing is when you basically you put something like a web application on the internet and you have, or on a server, and you have your customers test the program. It could also be you go out to the customer, install it in their environment, for example, and have them test it. I've done that on some occasions. So you basically go out, you install the software, they do some acceptance testing, and they come back with when they are done with it, basically. Regression testing. This is something that's usually it's usually done manually as well. Regression testing can be are most likely internal. It's basically you run through the whole program to make sure that nothing is broken. So it's like you have done all your unit tests, you have done all your integration testing, you've done some system testing as well, but a new version is coming out, so you need to make sure that certain parts of it that's hard to unit test or integration test, for example, is tricky to do in certain aspects. So you might need to do this regression testing. So regression testing is about like a green flag. Okay, yeah, it looks like it's working, so thumbs up, sort of. But it's usually quite exhausting. This is basically what we did at SPCS as well, because we needed to verify that, okay, this version that we send out, it still works. You can still do like an invoice in the system, basically, and it should print and look okay, for example, on the printer. So those are the kind of things that. All right, testing types: black box testing, white box testing, smoke testing, random testing. Okay, so we'll go through this pretty quickly. Black box testing is when you don't know the code, basically. You test something, you send something in, you get an output, but you don't know how the internal working of it. So we might know that it should return the square root of something, so we can do different values here in order to make sure that it works. So we don't know what's inside the box, basically. So we have to go through the specifications, take a look at that. Okay, it doesn't match our expectations. White or glass box testing is where we actually know the workings on the internal. So in these cases, we can make sure that we exercise all the if statements, all the parts, because we want to be able to. So back again to I forgot the word. So basically, you want to test as much as possible of the functions, basically. So so if it has a lot of if statements, you need to write test for all the if statements basically in order to get coverage was the word I was looking for. So good coverage of the functions. So if you can, you should write it for all the test cases that are easier to anticipate the behavior here, basically. So yeah, but we need to verify this again from the specification, because if a programmer has misinterpreted specification and done something wrong, we need to be verified, because we could write the test that actually works but is actually wrong towards the specification. So we need to match that as well, basically. So smoke and random testing, yeah, built on that the system may crash and be designed to crash when a faulty state indicates. So input run crash. Okay, so that's a lot of so basically smoke testing is you deploy a version of your system, or you run a version of your system, but you want to verify that it doesn't sort of go kablooey. So, and that can be different things. It could be like, okay, shit, it runs 100% of the CPU. That shouldn't happen, basically. So that if you do that, you probably want to install something locally and run that program. If it goes like the CPU goes 100 and doesn't go down, something is wrong, right? So if you smoke testing a web application, for example, can be you launch it and then you log into the system, you click around and see if everything works, stuff like that. So that can be a smoke test, for example, to see that, okay, yeah, the deployment seems to be working. So that's usually about the smoke testing part. So it's like a verification. Okay, everything seems to be working as it should. Okay, random testing. Here is like we send values to. Usually, this is something that testers love to do. Basically, they want to crash your system. So these are the tests that we developers might don't think is so funny. But I've had testers that, oh, if I send this super huge file to the system, what happens then? So yeah, we didn't think about that. So thank you for that. So we have to figure out how to fix that. So basically what random testing is, that is you test the forms with random values, or you send random values in order to figure out, does the system actually crash here? Or so instead of controlled values, we randomize the values and see what happens. So this is usually done by a tester. So like super big files. Oh, if I send a 1 gig file here, will it still work? Stuff like that. Or if I put Romeo and Juliet in your name input, what happens? Stuff like that. So yeah, those are kind of things. All right, so that's pretty much it. A lot of terms, terminology, basically. I like I said, I highly recommend watching Daniel's recording as well, because he might say it slightly different than I do. We come from 2 different perspectives. Next step for you guys right now is to watch the study guide. You go take a look at the study guide for this week. I highly recommend keeping up with the study guide in order to do it. Then it shouldn't be a problem actually doing it. So some of the videos there can be quite old, but they contain values still valuable. So do watch them through. So, and I will see you next time. Thank you.